Welcome back to The Explainer. Today we're diving straight into a really fascinating topic from the Cambridge IGCSE Computer Science syllabus, specifically Section 5.2.2 on blockchaining. We're going to decode exactly how this decentralized database technology fundamentally works. It's one of those concepts that sounds incredibly complex at first, but we're going to break it down into super clear, easy-to-grasp building blocks.
So just think about this for a second. How can thousands of people share the exact same digital record, perfectly synchronized and completely secure, without having a single central computer controlling the whole thing? For decades, we've relied entirely on central authorities, like banks or government servers, to manage our transactions. But suddenly, this new technology comes along and completely removes the need for that middleman. It's wild.
Here's our roadmap for today's explainer. First, we'll look at the decentralized database. Second, what's actually inside a block. Third, linking the blocks together. Fourth, how a blockchain works in practice. Fifth, proof of work and miners. And finally, a quick summary and recap.
All right, let's jump right into Section 1, the decentralized database.
Let's contrast how things usually work with how a blockchain works. Imagine a traditional centralized system. Say you and 3 friends go out to dinner, and the next day you need to pay each other back. If you use a normal bank app, all those money transfers literally have to pass through one central authority. But what if the bank's servers go down? Or worse, what if a hacker targets that single server? Everything grinds to a halt. It's a single point of failure. Now compare that to a decentralized system. Instead of relying on a bank, everyone in the network holds a copy of a shared public ledger. Every single transaction is transparently recorded on everybody's computer. No single central server means absolutely no single point of failure.
And that brings us to our core definition. A blockchain is simply a decentralized database that is strongly resistant to alteration, where all transaction data is shared among interconnected computers in a network. And that strongly resistant to alteration part, that is absolutely crucial, because there isn't one central server. A hacker can't just break into one database and secretly change a record. To pull that off, they'd literally have to change the record on every single computer on the network at the exact same time.
Moving on to Section 2, inside a block.
So what exactly is inside one of these blocks? Well, think of a block as a digital container. Every single block holds 3 essential things. First, you've got the data itself, so things like the sender, the recipient, and the amount being transferred. Second is the hash value. Now, you can think of the hash as a unique digital fingerprint. It's generated by a super complex algorithm, something like SHA-256, and it uniquely identifies that specific block. And the third component? That's the previous hash value, which is literally the exact digital fingerprint of the block that came right before it.
Now you might be wondering, if every single block contains the hash of the previous block, what happens with the very first block ever created, right? Well, that brings us to the Genesis block. The Genesis block is the absolute starting point of the entire ledger. It's completely unique because its previous hash value is simply 0. There's obviously no preceding block to point to, so it essentially acts as the anchor for the entire system.
Okay, let's look at Section 3, linking the blocks.
This is where the core genius of the whole technology really shines. That previous hash we talked about, it acts like digital glue. Block 3 contains the exact hash of block 2, and block 2, it contains the hash of block 1. So, because each block mathematically references the one right before it, they snap together to form this permanent chronological timeline. That chain of interconnected blocks is our shared ledger.
But what if somebody tries to game the system? Let's say a hacker attempts to secretly tweak the data in block 2 so they can pocket a little extra money. Well, the very moment the data inside block 2 is changed, its hash, its unique digital fingerprint, instantly changes along with it. And here's the catch. Block 3 is still sitting there looking for the old hash. Suddenly, the previous hash stored in block 3 doesn't match the newly altered hash of block 2. Instantly, the connection is completely severed. The chain breaks, and the entire network flags that tampered block is invalid. Game over for the hacker.
All right, let's zoom out a bit for Section 4, how a blockchain works.
Let's quickly walk through the real-world journey of a transaction in 5 steps. Imagine Phil wants to send Jack 2 Bitcoins. Step 1, Phil initiates the transaction using his secure private and public keys. Step 2, a brand new block is created that represents this specific transfer. Step 3, this new block is broadcast to the entire network, and all those interconnected computers jump in to verify that Phil actually has the 2 Bitcoins to send in the first place. Step 4, once it's verified, the block is permanently added to the chain.
And finally, step 5, everybody's ledger gets updated and Jack's wallet receives the funds. It all happens seamlessly and totally without a bank in sight.
But hold on a second. If computers today are incredibly fast, couldn't some hacker with a supercomputer just recalculate a fake chain in a matter of seconds? Great question. Let's tackle that in Section 5, Proof of Work and Miners.
So, to stop those ultra-fast computers from just instantly rewriting the chain, the network employs what we call miners. You can kind of think of miners as the network security guards. They are special users who run complex cryptographic algorithms to solve incredibly difficult math problems. And it's only when that problem is definitively solved that the new block can be verified and added to the chain. Now, for putting in all that hard computational work, miners actually get rewarded with newly generated cryptocurrency.
And that brings us to the actual answer to our supercomputer problem, proof of work. You see, the math problem that these miners are trying to solve, it is deliberately designed to be intensely, brutally difficult. It generally takes the network roughly 10 minutes of heavy computation just to find the proof of work and validate a single block. So that 10-minute delay, that isn't a glitch or a technical flaw at all. It's actually a really brilliant built-in security feature.
As our source material points out, the whole process of creating new blocks is intentionally slowed down, specifically to foil hackers. Because of this proof of work, if a hacker actually wants to alter a block, they don't just have to recalculate a single hash. No, they have to recalculate the proof of work for that block, and then the next block, and the next block, taking about 10 minutes per block. And they have to do all of this while the rest of the honest network is constantly moving forward, adding new, valid blocks. So practically speaking, it makes maliciously rewriting the chain mathematically and physically almost impossible.
Okay, let's wrap this all up in Section 6, Summary and Recap.
So here is your rapid-fire study guide for Syllabus Section 5.2.2. Just remember these 5 core takeaways. 1. A blockchain is a decentralized database, meaning absolutely no central authority is in control. 2. Every single block contains data, its own hash, and the previous hash. 3. A hash is simply a unique digital fingerprint generated by algorithms like SHA-256. 4. The Genesis block is the very first block in a chain, so obviously it has no previous hash. And 5. Proof of work is that deliberate computational delay that completely secures the chain by slowing down block creation.
I want to leave you with a thought to chew on. We've just seen how blockchain brilliantly secures cryptocurrency like Bitcoin without ever needing a central bank. But at its core, this technology is really just a highly secure shared database. And right now, it's already being explored for things like smart contracts, securing pharmaceutical supply chains, and even running whole voting systems. So if we can successfully decentralize money, what other central authorities in our world might this technology completely disrupt next? It's pretty mind-blowing when you think about it. Anyway, thank you so much for joining me for this explainer. Keep learning, keep asking those big questions, and I'll see you next time.